Welcome to Process Analytics. This is Dr. James Rowe from Roller College of Business at Rowan University. We now arrived at the last phase of the deming process, control phase. Once you identified all the improvement plans, it is a time to lay out ways to control the process and maintain the quality. One of the danger of process improvement is that it goes back to the previous state if not managed and encouraged carefully. So, in this lecture, we will discuss the importance and ways of control improvement plans. Module 4 covered improve phase and also it embraces control phase. In control phase, we'll revisit statistical process control chart that we discussed in Module 2 under the theme of process capability. Then we'll talk about total productive maintenance. Lastly, we will dwell on the topic of how to sustain improvements. Look at what Edwards Deming said about control. He said, a state of statistical control is not a natural state for a manufacturing process. It is instead an achievement arrived at by eliminating one by determined effort, the special causes of excessive variation. This quote by Deming tells us that controlling improved processes is not natural, but takes much effort to maintain and sustain it. Entropy is the law found by physicists. It is applicable to businesses as well. If not managed, the control is scarcely found, and a business loses quality and discipline. Control phase is all about maintaining and sustaining improved processes so that it may not relapse into the previous condition, but keeps on moving forward. We did talk about SPC in Module 2. There, the focus was on charting X-bar and R graphs. In this session, however, we will delve into different types of SPC and how to analyze them. First, let's think about why SPC is necessary for control phase. First, variations, especially assignable causes, are the ones that disrupt a process. Statistical process control is designed to detect both natural and assignable causes through mean and range chart. It's very useful. Second, once the system is in place, statistical process control can continue to monitor a process. It visualizes a process and people can see what is happening with the process. Third, statistical process control chart can be used for a variety of variables, including attribute variables. Fourth, experts in SPC can tell whether a process is heading toward a mishap or not. SPC can be used to predict the short-term future of a process. Fifth, however, SPC comes with cost. It can be expensive to measure and monitor key performance variables and process metrics. If there are too many variables to monitor, it can be frustrating to the business as well. Types of control charts. There are many types of control charts depending on the nature of variables or attributes. X-bar R chart is one of most well-known chart. When data is readily available, we use that. Run charts are used when the data is limited and only has single point data. MX bar or MR, that's a moving X bar or moving range chart, is also used when we have limited data. X moving range chart is also used when limited data is available. X bar and sigma chart, when sigma is readily available, we use that. And we do have median chart and moving average chart as well. These are all charts for variables, continuous variables. For control chart for attributes, such as integers like people or defects, that's a 1 and 2, or proportion, we use this control chart. P chart, fraction, defective, then we use P chart. And P chart is number of defectives. C chart, number of defects. U chart, number of defects per unit. And this is an example of MX bar MR chart. And this is an example of C chart. So it looks different. Now let's get into SPC analysis. How do we analyze and understand the data? I thought this textbook is providing us with very good examples. So the first one is process average out of control. The first chart is average chart and second one is range chart, as you know from module 2. And we see that when there are points that go above the upper control limit, it's obviously out of control. And what is interesting is the distribution. So the range is in control. So the range is in control. However, the mean is going out of bounds, right? So it's moving, below and above the control limit. So this is the situation. Second situation is process variation out of control. So the mean chart is under control. However, range chart is out of control. What does that mean? Especially in this situation, the range is getting bigger and bigger. So if you look at the distribution of this process, it looks like this. So the range is changing, mean is stable. However, the range is changing all the time and it's getting bigger and bigger. The third situation is average and variation out of control. So both mean and range are out of control. And what's happening here? So the mean is not stable, and also the range is changing here and there, right? That's why it's a terrible situation because we have to change everything. Fourth situation is process in control. So if process is control, yet it may be a little bit unstable. Why is that? If you look at this, average is moving and range is stable. However, it's also changing. So this process is under control. However, if you observe what is happening with the data itself and the distribution, you see that it's a little bit unstable, right? It's changing around. So even if it is under control, we see that there are some uncertainties embedded in the process. Here is a control chart in interpretation. First one is 5 common rules that I discussed from module 2. So I would not spend much time there. The second one is other unusual patterns. For example, rule 6 is stratification. 15 or more points in zone C. Zone C is a very good one, right? It's one of the best one. And if 15 or more points are staying over there, that means the process is too good to be true. So maybe there's something not measured right. So we need to look into that. The second one, rule 7, is mixture or systematic variation. So we see this graph is oscillating around the center line and very regularly. It looks too regular, uh, right? So too artificial. That's how we can see it. So it's not natural. That's how we can understand that. So we may need to look at this process because it does not look natural. Causes of variations. As we learned, there are two types of variations, assignable or natural causes of variations. And our goal from statistical process control chart is to identify the assignable causes. Look at these jumps in process level. So there is 2 points below, and then suddenly there's a jump between second point to the third point, and then from fifth point to sixth point, there's a jump. So it's just staying over there for a while, and then making a jump, and then making it jumping it down, and then jumping up. So jumps are in the process level. In this case, if this is an X bar chart, it may mean materials coming from different sources, right? So different quality of materials are coming in. As a result, when things or supplies are changing, then the process may become unstable and jumps are taking place. Other cases might be new operator or machine. New operators are or new shifts happen or new machines are used there. Modification of production method or process may happen. It would not happen very often, but it can happen. Change in inspection device or method may be another cause of that. If this is happening in R chart, range chart, it might be because in changes in material, changes in method, operator, and inspection, and so forth. Corrective action in this case is that keep material supply consistent. That's the first thing. And investigate source of material or operator or process capability or machine. Those things has to happen, have to happen. Second situation is recurring cycles. So just like business cycle, it looks very, uh, we see clearly a cycle here, and it's unnatural in process analytics. And why is this happening? We want to observe and do research about that. If this is happening in X bar chart, it's because physical environment is changing. For example, temperature, in the morning it gets cool and then it gets hot and then it cools down again in the evening, right? In that case, the environment itself is affected by the temperature, or the temperature is not cooling down very well, or you know operator is working energetically in the morning and then lose the productivity and then picks it up later. The kind of tired operator might be another reason to see this cycle. Regular rotation of machine or operator is another good reason to suspect. If this is happening in our chart, then it might be because scheduled maintenance is happening periodically, or it's because tiled operator or tool wear, because of that it's happening. Corrective action is that if environment is the issue, then we have to adjust and control that. Service equipment or rotate operators might be another thing that we can do. Evaluate machine maintenance and replace, sharpen, or repair tools are other options that we can consider. Third situation is points near or outside limits. Um, it's always good to have these points around the center line, and if it is approaching the boundaries too closely or even go out of the bound, then it's clearly a bad sign. And why is that happening? In X bar chart, it happens because of over control. That tire, we try to control it too tightly, then it might happen. And large systematic differences in material quality may be a cause of that again. And large differences in test methods or equipment could be another reason. In range chart, if this is happening, it might be because of mixture of material or distinctly different quality. Corrective actions can be as follows. Check control limits. If you are trying to control too tightly, you want to, give a leeway for the control limits. Investigate material variation. And, is it because the material is not stable? You want to look at that. Evaluate test procedures or evaluate inspection frequency. or eliminate operator over adjustment of the process. Those things can be done. Fourth situation is lack of variability. Again, we have the center line. It looks very good because the dots are not approaching the boundaries at all. So it looks very good. However, the variation is kind of very small. And why is that the case? If this is happening in X bar chart, it might be because incorrect calculation. In other words, the upper or lower control limits are too big because of calculation error. On improvement in the process, somehow you implemented a new process or corrected it, and that works very well. That might be the reason, and if that is the case, that's very good thing to see. And employee may not be making checks, so although the reality is different, the employee is not really doing the work or monitoring the process very well. That's why it looks like a good, but actually it's not happening. If this is happening in our chart, collecting measurement from widely different lots could be a cause of that. Or improvement in process since limits were calculated could be another reason for that. Corrective action for this case is checking control limits first. I think that's very important. Second, validate rationale sample subgroups. If subgroups are too divided or too small, it might be happening. And verify checking procedure, gauges, and other things, suspecting the tool problem. Verify proper employee measurement can be another option. And lastly, congratulate someone for improvement if this is the result of improvement. Here's a question. A control chart is used to A, determine if defective parts are being produced, B, measure process capability, C, determine causes of process variation, D, detect non-random variation in processes. The biggest reason why we use control chart is to find the assignable cause, which is D. So the answer is D. Next question. A process has been experiencing problems lately. The operators charting the process have identified the cause to be due to a change in incoming materials. This problem is A, attributed to purchasing, B, a special cause, C, a common cause, D, a normal event. So this is something that we can um, identify as a assignable cause. So we can say that this is a special cause. B is the answer. Next question. The vector D4 in X bar and R control chart is used to A, determine the upper control limit of a range chart. B, establish the control limits for the average chart. C, correct the bias in estimating the population. D, determine the low control limit of a range chart. The answer is A, determine the upper control. It's a D4. Um, if it was D3, then the answer should be D, right? Determine the lower control limit of a range chart. Next question. An X bar and R chart was prepared for an operation using 20 samples with 5 pieces in each sample. X bar was found to be 33.6 and R bar was 6.20. During production, a sample of 5 was taken and the pieces measured 36, 43, 37, 25, and 38. At the time this sample was taken, and what is the answer? If you calculate the X bar chart and R chart in this case, you will see that D is the answer. Only the range was outside the control limits. Lastly, this is a tough question and it takes some time to calculate. If you like to, you can use Excel to make calculations, but it's fine if you want to use a calculator too. So you have the data, 5 samples, 5 lines, and you need to calculate the X bar chart and R chart here. And you need to find out the sample means and the mean of sample means and apply the formula D5 A2 uh, after finding that and calculate upper control limit and lower control limits, and the answer will be D, 23.65 and 16.35.